Hi, I'm Roger Aines, and I'm going to talk to you today about encapsulated liquid microreactors. Challenge in chemical engineering is to make the reaction occur the way we want it to and not the way nature wants it to. For instance, in carbon dioxide capture, it's easy to get a liquid that grabs the CO2, and we want that liquid to have little tiny droplets so it has a large surface area so that it can grab it very quickly. The problem is the liquid wants to form into large raindrop-sized droplets, and so we can't use this kind of system for carbon dioxide capture. It's not fast enough. On the opposite side of the ledger, we have a problem when we want to add a reactive liquid into another liquid. For instance, if we want to use acid to clean off rust on metal, the acid wants to disperse. When we want it to be concentrated, we want to put the rust exactly on we want to put the acid exactly on the rust. Now, biology handles systems like this all the time. They build structured systems at a perfect size for diffusion. For instance, in your lungs, you have gas, the air you're breathing. Then you have a liquid, blood. In between, you have a membrane that carries a catalyst that helps CO2 move across that membrane rapidly. And all this is done at exactly the perfect size for diffusion, about 200 to 500 microns. That's the magic size where it's large enough to be reactive and not too reactive, but small enough to be rapid. Well, what if we had this kind of exact control over the reactivity of liquids? Our concept is to encapsulate liquid solvents in a polymer shell with adjustable permeability. On the right, you see some of these on someone's thumb, methylethylamine filled microcapsules, which is the amine that's used for carbon dioxide capture today. They have greatly increased surface area. They can tolerate any kind of liquid you want inside, and as you can see, the liquid doesn't get outside, so it's much safer. They also tolerate precipitation, which allows us to have new chemistries and also to add catalysts to the system, start looking more like the kind of complicated system you saw inside your lungs. The system ends up behaving like a solid, but it still has the liquid capacity, so it's a dual benefit, behaves like a solid, but has the capacity of a liquid. We originally created these for RPE as recyclable high surface area reactors for concentrating carbon dioxide. We make them by a microfluidic inkjet technique. The wall is silicone, the same silicone rubber that you have in the red spatula in your kitchen. Inside we have a solvent that has a color indicator in it so that as the carbon dioxide is absorbed, the bead turns color to see that it's fully loaded. They're fully recyclable. We heat them up after they're loaded to get the carbon dioxide, now purified carbon dioxide, back out again, and we can recycle them hundreds of times to temperatures of up to 200 degrees centigrade. Most important thing is the large surface area. They're about 400 times larger in surface area than the equivalent amount of liquid would be if it were put into a packed tower, which is the way that a chemical engineer would normally do this kind of reaction. Now, this is a game changer in carbon dioxide capture, because it allows us to use efficient solvents that are very low toxicity. On the left, you see our beads absorbing carbon dioxide. There's two forms of the beads there. We have, on the lower left, beads with catalyst in the shell, and on the upper right, beads without a catalyst. And you see that the ones with the catalyst turn color faster as CO2 passes over them. But eventually, they all turn yellow as they have the same capacity. The catalyst just affects the rate at which the carbon dioxide is absorbed. This allows us to make now a new carbon dioxide capture system that uses basically baking soda as the solvent. It's the same baking soda that you have in your kitchen cabinet. So it's a low toxicity, inexpensive, and also very low energy carbon dioxide capture system. It also lets us do something really cool. We can precipitate solids inside these shells. You see precipitating inside the silicone shells here. It's the same bicarbonate that you have in your kitchen. As carbon dioxide goes through the shell into this liquid bicarbonate inside, eventually the concentration gets high enough that a precipitate begins to form. That precipitate is just the baking soda that we talked about before. This is really nice, though, in chemical engineering process that it's all contained inside the shell. You see they're all now exactly the same size, and they all have exactly the same properties. Something else really cool about this, and that is that the excess water inside gets expelled. When you look at the lower right picture, you see that the shell has dimpled around the solid. It's basically shrink wrapped onto the solid because the water has been expelled through the shell, and all that we have left is just the solid inside. It's a pretty neat way of making small encapsulated solids. This microcapsule production is now routine. We make them with this inkjet technique. And the most important thing about that is that they're all exactly the same. When you want to design the shell, you can have the exact same permeability in every one because the shell is the same thickness. They're all the same strength. And we can design them with many polymers to have chemical compatibility and handle different kinds of chemical systems equally well. One last thing. We can trigger the release from them by two ways. We can adjust the permeability, as you saw where we had permeable shells that let carbon dioxide go through them or could let other chemicals or gases go through them. But we can also adjust the shell so it actually breaks at external signal. For instance, temperature is one that you could imagine. Or imagine that you wanted your shell containing acid to break when it reached the rust on the metal so that you deposited your acid only in the perfect place and you used the exact right amount of acid and exact right place. We're talking about a variety of applications for these encapsulated micro-reactors. The Navy is interested in using these to make new rebreathers for their divers. We're, of course, talking about using these in a variety of gas detectors and getters, where the gas makes a color change so you can see when you've absorbed a gas, but you can also use it to separate gas, as we're doing with carbon dioxide. You can do that with a variety of gases. We're very interested, though, in new uses. And those kinds of new uses are likely going to start with things where there's a liquid that already does a job that you're interested in, but it's not easy to handle that liquid. And now you can encapsulate the liquid in these small beads and make it able to be handled in the form of a solid, which would open up new applications for the liquid that already exists. We're very interested in discovering new applications and working with new partners to develop those applications. If you have questions about this technology, please contact the Industrial Partnership Office, Leah Rogers.